Okay, Mr. Dixon. This is test corrections part 2. This is about forces. Okay. So, first question. A train is at rest and inside the train a drone is on the floor. The train accelerates for some time and then the drone is brought to hover. What happens to the drone and why? So, this relates to the first law of motion, which is inertia. This is basically states that an object in motion will stay in motion unless acted upon a outside force. So this relates back to the question. It says a train is at rest and inside the train is a drone on the floor. The train accelerates for some time and then the drone is brought to hover. What happens to the drone and why? So this happens, so the drone will continue to be in motion. This is my answer. Unless it is acted upon an outside force. So basically the speed of the train will travel at a certain speed. Then the object or the drone will continue to move. Like continue to move at whatever speed it was. Okay, so that's my answer. This part. Number 2. Okay. A train is at rest and inside the train a drone is on the floor. The drone is brought to hover and then the train accelerates for some time. What happens to the drone and why? Well, this will also relate to Newton's law. And when the train is my answer. The train accelerates for a certain amount of time. The drone will go opposite direction of the train. The reason is the force of the train is going faster, which causes the train to go backwards. Okay, this is okay, that's the answer. Because the question is saying the train is at rest and inside the train is a drone on the floor. The drone is brought to hover and then the train will accelerate for some time. What happens to the drone and why? So the train will accelerate at a certain amount of time. The drone will go the opposite direction. The reason is because the force of the train is going faster, which causes the train to go the opposite direction, or goes backwards. Because it's the opposite reaction. This is relating to Newton's I think it's, wait, let me get my books. Newton's third law? Yeah, Newton's third law. This is Newton's third law. Okay, Newton's third law. Okay, number 3. Number 3, I got part of it. I got partial credit. I didn't get full credit, but I got partial credit. A train is moving at 60 miles per hour. Inside, we see a boy safely playing with the drone that is in midair. The boy is directly behind the drone and is facing the front of the train. The conductor notices a car on the track about 0.7 miles away and immediately hits the brake. What happens to the drone and why? So this relates to Newton's first law. If an object is in motion, it will stay in motion unless acted upon an outside force. So let's see, draw a picture. So the train is, this is a train moving 60 miles per hour, and inside there's a boy. So inside is a boy. Is playing with the drone midair. The boy is directly behind him. So this is a drone. I don't know. That's a drone, and he's directly behind it, facing the front of the train. So there's a distance. So it's like 0.75 miles away. And then suddenly there's a break. So this will cause, so basically this would be if the drone moved forward and it stopped abruptly due to a train, then it will continue to move forward at 60 miles per hour with the direction it's moving of the train. So this is Newton's first law. This is my explanation. If the drone moved forward and it stopped abruptly due to a train, then it will continue to move forward at 60 miles per hour with the direction it's moving. Yep. Okay, that's number 3. And I'm gonna go to number 4. I mean, no. Oh wait, actually, this is 1A. Sorry, this is 1A. This is 1B. This is 1C. That's not 1, 2, 3. It's 1A, 1B, 1C. And then let's go to number 2. Number 2, it says, I got only no credits of this because I didn't do it right. It says draw a force body diagram of all the forces acting in this picture while the soldier is shooting. Why is this a bad idea? So this is a picture of the guy on the boat. So this was my picture, but it was wrong because this is for an incline. This is not for a force body diagram. So since the guy is sitting in the middle, this is him. there will be always gravity acting upon it. So it'll be force gravity. And to the left would be the force of the boat. And then to the opposite direction would be force of the gun. Because if he's shooting the gun, like he's pulling force back on the gun this way. So there's going to be force when you pull the gun back before you shoot. And it will be force acted upon on the boat on the other side. So there's opposite reaction. And then the top would be the buoyancy. So that's basically the force of the water. That's opposite to the force gravity. Okay, so that's 2. And the next page is a different one. It's 1A. It's another 1A problem. Okay, so it says a mass. Okay, let's see. A mass M is placed on an incline that makes an angle of theta degrees with respect to the horizontal. The coefficient of friction between the mass and the incline is mu. Draw 2 force body diagrams for the above system, one with and one without components. So I got partial credit. So this is the incline. This is theta. This is M. That's the mass that is placed on the incline. So the one with the components is this, and will be force parallel. Weight parallel, and this will be weight perpendicular. This will be newtons, and this will be force. This is with components. Okay, without components. Without components would mean that there would be no weight parallel, weight perpendicular. There will be no weight parallel and no perpendicular. So it will look like this. This will be there will always be weight equals mass times gravity. And then this will be the force of the force of the mass that's placed on the incline, and this will be the newtons. So this is without components, and this is with components. Okay. Okay, so then this is 1B. Okay, derive an equation for the acceleration to the, derive the equation for the acceleration of the mass. So it will be F net. No, actually, well, A equals F net over mass. That's your acceleration, excuse me. So you would have also F net equals mass times gravity sine theta minus mass times gravity cosine theta mu. Now mu is the sum of all force. F net is the sum of all forces. So basically F net will equal to the sum of all the forces acting upon the force. Okay. Mu is the amount of friction. I'm gonna highlight this so I know. So this is okay. So you're trying to derive to get acceleration. So you would get this. So it would be F net equals mg sine theta minus mg cosine theta mu. And excuse me. So then you would divide that by m to get rid of the mass, because you don't need mass. So then you would get gravity sine theta minus mg cosine theta mu. And this will be in parentheses. You divide by mass because you don't need mass, because you're trying to find the acceleration. So then what you have will be A equals F net over m. So your equation will be g sine theta minus cosine. I don't know why I'm cosine theta mu parentheses. Now you don't really need this g because it's on the outside too, so you don't need this g. So let me just cross that out. So this is your derived equation for acceleration. Okay, so I'm gonna leave this aside because we're gonna need this for the next problem. The next part. So this is 1C now. Find the acceleration. No, actually, never mind. I got this right. Never mind. Okay. Never mind. Okay, we'll do the next problem. So 2A. Draw of force body diagram for the above system, one with and without components. So this is what I drew, and I only got partial credit, which is 1 point. So I'm gonna use this to redraw my components. I mean my force body diagrams with and without components. Okay, so I'm gonna redraw this again. Okay, so this is an incline, and this is lowercase m, or I could just label M1. And there's like a little rope, this little thing attaching a box. This would be capital M, M2. This is tension. This label as tension. Pulling on a rope. And this is this theta. Okay. Okay, so draw two force body diagrams for the above system with and without components. So I'm gonna do the one with components. So this will be the and the incline in the middle. And there's always going to be N pulling that way. There's always going to be weight parallel because it's going this way. Because if you draw this and you split this into the components, this will be weight parallel, this will be weight perpendicular. Because that's when you split the incline into two components. This will be weight parallel, weight perpendicular. And you always have your force pulling on the box, which is the tension. And this one will be weight perpendicular. So that's with components. Now, without components, so I'll just do without components here. Oh, N is force normal. Yeah. F is friction. I forgot to label it. Friction. Friction is pulling on the rope is tension. So without components, this is the object in the middle, the incline in the middle. It's always going to be weight equals mass times gravity, pulling the incline down. And then I have one arrow here. This is force normal. And this is F, which is friction, pulling from the rope. So this is one without and one with components. Okay, so okay. Derive an equation for acceleration of the system including friction. So it's not the same, but it's similar to this question. But this question had just only asked for acceleration, but this is this next one I'm doing is dealing with including friction. So that's two different things. So I'll still use A equals F net over M. So what I'll do is mg sine theta minus mu, can't forget mu, mg cosine theta, parentheses, over M. And to break this down, F net equals mg plus weight perpendicular minus weight parallel minus F plus N. Now this is the components of the F net is the sum of all forces. And basically when you draw a force body diagram, this is all the components of for the sum of the forces. Mg weight perpendicular parallel force and force normal. And then what you would do is weight perpendicular will cancel out with force normal because you don't really need that, and that's the opposite of cancel out. Well, Yeah, but that will be opposites. You cancel those off. So what you have is F net equals mg minus weight. Oh, what I keep writing? Weight parallel minus F. Yeah. So this is your equation for with friction. This is with friction. Okay, so the next one you will have to use this equation to plug into solve for. Okay, so this is the equation I'm going to use. So it's given me mass equals 51 kg, m equals 101 kg, mu Hey Tyler, can you unlock your phone? Oh, never mind. Okay. So your mass is 101 kg times the gravity is 9.8 meters per second squared minus your weight minus, wait, what? Oh wait, theta 31. I forgot about that. I'm looking at the wrong one. Weight parallel. Wait. So am I doing this the wrong equation? Minus 51 sine theta 0.21 cosine. Wait, 21 is mu. I forgot about that. Oh, 51. Yeah. This is, wait, let me label what's on the top of each. It's mass, mu, and cosine. So when you plug this in the calculator, you get 26.27, and you get 4. No, actually, no, you get 9.180. You add that up. You get 101 plus 51 equals 4.23 meters per second. Sorry, kind of messed up. Yeah, kind of messed up. Okay. There'll be a part 2 tomorrow.